Right. So, okay. So now we have settled with the definitions of the inner product. So now we will have a look at how the inner product can also be used to calculate the length. Okay, and also in last 2 weeks, I did mention to you that uh, that the concept of angle, length, and distance in the inner product can turn the R2 and R3 into Euclidean spaces. Okay, so basically, um, we usually knows the formula to measure or to calculate the length by using the Euclidean sorry, we know the formula to calculate the length for the Euclidean space. Okay, so now we will see the relationship between the Euclidean space and the inner product space. Okay, so now okay, all right. So now I will introduce to you the term norm. I'm not sure whether this term is new or not for you, but yes, I will just mention it to you. So we do have a term norm, or we can also call it as length. Okay, length or norm. Okay, so we have nem, nem pula ni, norm or length. Right? Okay. Right. So definitions here. There is a definitions here. Okay. Definitions. So we let V to be an inner product space. So when we say that the V is in an inner product space, meaning that there is an inner product operation happens in that space. And we define for every V in V for every V in capital V, we will get V equivalent to square root of inner product V and V. Okay, and this V here is called as normed space or norm lah. Okay, usually we will just mention this double bar V double bar as norm or length. Alright, so and this norm and okay, wait. This is okay. Oh, naik. Okay, alright. So again, now we know the operation for the norm. Alright, for this one. So again, because the V is in an inner product space, and remember we have the three axiom. The first three axiom in our first slide here. So meaning that this norm also satisfy that axiom, that three axiom just now. Okay, sorry, these three. So we can prove it. So the third axiom just now mentioned that the inner product of vector V is greater or equal to 0. This one, the positive definiteness. So remember, norm is length. You will never ever get length to be negative. Okay, you tak akan tahu, you kira-kira panjang kotak tu bersamaan dengan negatif 10. Impossible. The length, the symbols kita panggil it a symbol kot no? Symbol. The symbols for the length, it must be greater or equal to 0. It must be a positive value or 0. Okay? The norm or the length will be 0 if the vector V just now is 0. If it is not 0, okay, if let's say it is a real number or if it is a complex number, when you do the proving, when you do the operation, at the end, you will still get real value. You akan dapat juga positive value. Sebab apa? Sebab the norm or the length just now, it's occur in the inner product space. So bila dia dalam inner product space, dia mesti mematuhi 3 axiom ini. Clear tak yang itu? Okey ke semua part yang itu? Dapat? Okey tak yang itu? Okay. Yang tu. Okay, so that will be the first proving. So the first the first proving. Kenapa kan? Okay. So now let's say we try to apply the third axiom first. Okay. So we can say here saya tulis kat sini 3. So dia merujuk kepada axiom yang ketiga lah. Okay. So okay. So by axiom 3, alright, by axiom 3 of the inner product, okay, we know that the inner product of V must be equal or greater to 0. Alright? Okay, therefore, we can say that the norm of V is well defined. Okay, so meaning that it shows a logic here. Okay, because we say that the norm of V is equivalent to the square root of inner product V. And remember, the square root, if you have the square root negative 10, it will give you apa term itu? In real number kan? Unreal number. Bukan ada number apa lah. Indefinite numbers. So the square root will only give you a real value if it is greater or equal to 0. Okay ke yang itu? Okay, the second one, okay, we can say that this one, okay, this one does not, the second remarks here, this is for the remarks, the next remarks here does not relate to the axiom, but we can say that the norm is actually coincides with the standard or usual Euclidean length in R2 or R3. Okay, so this should be R to the power of 2 and R to the power of 3 lah. Okay, so we will look into this nanti, later. Okay, I will show to you how the norm, this formula here, it can be similar to the Euclidean length. Alright, and the next one is, we can say that this, the norm here, right, is indeed a norm. Okay, this is macam funny sikit lah. Okay, this yeah, this one, the norm here is indeed a norm as it satisfy these three axioms. So these three axioms is actually quite related to the first three axioms for the inner product. Okay, so the first axioms here is related to the linearity, where we have this norm with, let's say, A with vector V, and the A is the scalar, and this actually is equivalent to modular A multiply with vector V. Alright, and the second axiom, this one is related to the definite positive too, which the V, the norm V is greater or equal to 0, and if the norm is 0, then meaning that vector V is 0. And the third one, okay, the third one here, U plus V is less or equal to norm U plus norm V. This is actually relates to the triangle in equality. Alright? Okay, so now we will do the proving for these three axioms here. Okay, so for the second one here, it is not that difficult, because for the second axioms here, we can use the axioms number 3. Okay, axiom number 3, the positiveness, and we will try to have a look for this one, the first one, the first axiom there. Okay, so let me copy this one and bring it to here. Kita boleh okay, so for this one, okay, we have A with vector V, and this is equivalent to modular A multiply with norm V. Alright, how are we going to prove this? Okay, So we will start with the definitions of the norm. Okay, so for the norm, we know that the operation for the norm is equal to square root of inner product AV. Okay, so here actually this one actually you can get something like, okay, this is the A, B. So what you can get here is square root like this, and then AV, gitu. Okay, so you will get something like this. Alright, so if you notice here, okay, this is the inner product, and the inner product for the first component and the second component, there is a scalar here. So for the first component, if you refer back for the first component here, you can refer to the axiom 2. Okay, so for the axiom 2. So axiom 2 say that if we have a scalar here at the first component, then we can bring it out as it is. So in this case, we have the square root, and for the first component, we will extract out the A. Okay, so our inner product for the first component, it will left with V only. So what about the second component here? So if you remember, we do have, after we have the axioms, then we do the remarks for the axiom for the inner product for the second component. So for the second component, yes, for the second component, we still can extract the scalar here to be out from the inner product setting, but there is a bar here for the second component. Okay, so again, it will left with V for the second component there. Alright, so you will get something like this: square root with A multiply with bar A, and then you will multiply again with the inner product of VV. Alright? Alright, so remember here, so now we have these two special here. We have the multiplications of a real number with a conjugate. Okay, imaginary numbers there. So when we do the multiplications of these two different types of numbers here, it will give itself. Okay, in this case, A multiply with conjugate A, kita akan dapat balik A. Alright, we will get the A. Yes, we will get itself with times kita akan dapat diri kita balik with a power of 2. So from here, ini adalah teori yang conjugate times real number. Okay, so from here, by using that theorem of conjugate times conjugate number times A, then here we will get a modular or a positive A to the power of 2, and we will multiply it with inner product of V. Okay, then we can bring this A to, we can bring it out, and we will get modular A to the power of 2 square root inner product V. Okay, and remember square root of VV is equivalent to norm V. So from here, we will get A to the power of 2 square root V as norm V. So, sorry. This one kita dah bring it out, so we don't have the square root again. Okay, because we have settled with this one, so we do the operation. Sorry, we are not taking out the A, but we do the square root for the A, so we can cancel out the power of 2. Alright, so it will left with us the square root inner product VV. Gitu. Sorry, okay. So this one we do the operation for the to the power of, for the A to the power of 2. So we get this. So this one is similar with this one. So meaning that we have proof for the first axiom for this one. This one. Right? Oh, okay, so for the third axiom here, the norm u plus u plus v is less or equal to norm u plus norm v. This part is a bit tricky here, okay, because I am going to introduce to you another theorem here by Cauchy-Schwarz. Okay, the inequality, the Cauchy-Schwarz and Banniakerski. Okay, so this is settled with for the first one, for the first axiom, for the norm. So now if we want to do for the third one, just now it says that u plus v is less or equal to u plus v. Okay, all right. So this actually, yeah. This is what we are going to do, and we are going to use a theorem by Cauchy-Schwarz, and also someone with this name. I think this name I will Korsky. So these are actually two mathematicians that come out with their own formula or theory, okay, and that theory is this. A modular u a modular inner product of UV is less and equal to norm U multiply with norm V. Alright. So this is actually for the inequalities lah. Okay, the Cauchy squares and Bunyakovsky, they come out with this inequalities theory here. Okay, so okay, alright. So I will start for this one. Okay, so now we will show. So the aim is for us to show that the triangle inequality follows from the Cauchy. Macam mana kita betul? Oh, CS lah. CS. And the B just now. Okay. For the Bunyakovsky, it is not that well known. Usually people will say that they are following the Cauchy. Okay, so Cauchy squares, I make it short to CS. Okay, all right. So let's do this together. All right. Okay, so if you look back to the equations of the norm here, so the equation for the norm, it comes together with the square root. Okay, so it is better, but to make it easier for us for the proving, we can remove this square root. Okay, by applying square kuasa 2 kat sini. Okay, to both side. Okay, so now we have this x plus y. This is by definitions for the norm. Okay, x plus y is equal to square root norm x plus y. Alright. Okay, so to remove this, we will add x plus y to the power of 2 here. Okay. Okay. So by having that kuasa 2 ni, so we can remove the square root here. So it will left us with x plus y. The inner product of x plus y X plus Y. Okay, so from here, okay, we can use the linearity, the axioms, the properties, the first axioms for the inner product. Okay, for the second axioms. The second axiom says that if you have x plus a scalar a, y, then it will be equivalent to x, y plus a, y plus inner product a, y. Okay, so this is the axiom for the second axiom for the first axiom. The second axiom for the inner product axiom. Gitu. Betul? This one. Let me check. Yes, UVR, WVR. Betul lah. Alright. So we can apply this to here. Okay, so what we will get from here, we will get something like this. So x, so we will get the inner product of x plus, mana tadi? Okay, x. Tambah xy tambah y x tambah y. Sorry, this is the this actually for the inner product xx, we can rewrite it as x, the norm to the power of 2 plus, okay, for this part here, okay, for this part here, the first one, the inner product for the xy is the real product, and this one, we can rewrite it in the form of the first one by adding the conjugate here. So for this part here, kita boleh highlight kat sini. Okay, so for this part, let me change it to the red color. So for this part here, okay, for that part, the yx, we can write it in the form of xy by having the conjugate here. Okay, so from there, okay, this one, we will have xy plus xy with bar plus norm y squared. So this one, I need to add bar here, right? Okay. Okay. So from here, then I will just copy. Copy this one. Then this part, okay, this part, because it is a real number plus a conjugate, kan, yang sini ni, the first one is the real number, the second one is the conjugate. So it is actually, we can rewrite this part to have, it is actually equivalent to 2 real number of inner product xy. Okay, so this is actually from the properties of conjugate of complex number, the properties of the complex number. Yes. Sorry. Okay. Proceed. Okay. So for this, for the real number of the xy, okay, this one, because the real number, the real part and the imaginary part of complex number is always less and equal to the modulus of the complex number. Okay, so this is another property coming here for this one here. This one here. Okay, where this one, it will always give us less or equal to modulus of complex number. Okay, hence by having that property, we can rewrite this as, this is not equal dah, this is less or equal to modular of inner product x, y plus y. Okay, so here from the equation symbols, so we can now have our less equal by using the properties from the by using these properties, the combination of the real numbers and the imaginary numbers. Okay, then from here we can start to use our Cauchy scores. Just now Cauchy score says that the UV is less or equal to the UV here. So this is what score say. So score says so score says so score says this. So now add this to here. Okay. Okay. So now score says this. So now we can do something with our middle part here, where by using the Cauchy scores, so we can continue this part here, but we will modify a bit this one, where we can change the modular inner product here to norm x multiply with norm y. Alright, and this one is actually equivalent to x plus y to the power of 2. Okay. So now we can have or we can prove the third axiom just now. So now we can show that the x plus y to the power of 2 here is less or equal to norm x plus norm y to the power of 2. So we can cancel out this power of 2 by adding square root to the both sides. So we have this and we have this. Okay, we have to the power of 2 here, right? So we can add square root to the both side. Okay, then now we will get this one as in axiom just now. So it is proving. Okay? Okay ke? Okay. So I don't get time to explain about the distance actually, but I hope by now you can get the idea of the norm and the inner product. Okay, so I will prepare to you, I will share to you these notes. This one is a simplistic notes. Okay, I hope you can see this screen now, the inner product. So this one comes together with the examples, so you can have a look, and these notes actually explain more or less the same thing as what I explained to you. So we will look into the length and angles if possible next week, or I will prepare with a video so that you can watch, and then I will share to you some exercises, okay, on how to get the length and the angle. All right, so yes, I think that's all for today's class. Okay, any question? Any question? Apa soalan tak? Ni semua ada ke tak ni? Hello. Senyap je. Assalamualaikum. Assalamualaikum. Senyap. Senyap. Ada ke tak ni semua awak kan?
Ada.
Ya. Ada. Ada soalan?
Ada.
Tak
ada soalan, Doktor.
Betul, tak ada soalan ni.
Assalamualaikum, Doktor.
Nanti jangan dah thank you, belum lagi. Nanti jangan lupa you have task to do, okay, to prove. Mana tadi this one. To prove for the norm whether it can fulfill the second axiom or not. So you need to do that, and we will discuss. I will create a forum tab in the Putra Blast. So you can discuss there. You can share whatever you have done there, and you can discuss among you. Is that okay? Alright. Okay, so I think that's all for today, and for the length and angle tu nanti saya akan buat video lain lah untuk awak, macam dah lambat sangat kita ni. Okay? Alright. So yes, thank you. That's all. Thank you semua.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.